יש לי מה בדרך כלל אמור לעבוד, אה?
כן.
זה המחשב יכול לחבות לדעתי. חזור. שלום, שלום. הוא עושה משהו. רואים משהו כבר. עכשיו זה הדופית. עכשיו אני מנסה דופית וזה לא מול הרבה. זה הרקע שלי.
כן?
כן, עכשיו אוריה עושה דופית וזה מול הרבה. אוריה.
מצוין, יופי. חזרתי לנשום.
אני קורא לשים אינטור על הדוח.
מה קורה? מצאתם... אתה יושב. יושב.
גיל, בזמן לא ראיתי אותך.
כן, כן. טוב, פעם לא ראינו.
נכון? זה סימטרי, לא?
מה זה?
זה סימטרי, לא?
סימטרי. לא, יום חמישי לימדתי, לא חתולה.
אוקיי. אני עם 4 ילדים, באתי לשבוע וקצת, זה לא עובד ככה,
שבוע וקצת זה לא שווה.
שבוע וקצת עם 4 ילדים זה קשור לחלות.
כן, זה לפחות שבוע על כל ילד.
לגמרי, כן, משהו כזה. לגמרי.
מה קורה איתך?
בסדר? דיבורים רבות, די פחות אחד. די ברבות, כאילו החלק, מה? די ביד. זה לא Let's wait maybe 1 minute.
Sure. Then you're the boss.
מה שלומך?
אני פעם אחרונה ראיתי לך זה פלו אלטו או משהו, לא?
נכון, נכון, כן. 5 שנים אולי?
משהו כזה,
כן.
לא הרבה זמן, הגעתי אני לא זוכר. טוב, אחרי זה בואו אבל אמרת שבא לא, יש לי שיחה בהרצליה, אני צריך להימלט מיד. כן, אני לא זכרתי את זה, וקראתי זום זמן קורזת. זה היה שישי. יכול לעשות בשיחה הזו? כן, אבל קודם כל זה עם נום, הנה זה משהו שנינו נתחבר מלאכת. אני יכול בעיקרון. Okay, we're going to start. I'm very happy to have Shachar Lovett with us to give the second Erdős lecture. He will tell us about the combinatorial structure of Boolean functions. Please, Shachar.
Thanks, Yuval. By the way, I have a question. Do you not need a microphone or something for the Zoom?
The recording works.
It's okay, you don't need one. Okay, good.
It's a microphone.
Okay, good. Thanks everybody for coming. So, actually, before I start, just say that I partitioned this into 2 parts. So the first part is going to be on the slides, more like telling stories, and then going to be a break. And then the second part is going to be like proofs on the board. So if you want to escape after the first part, then feel free to do it. If you just want to stay for the stories, yeah, this is all joint work with Sasha Knopp, Sam McGuire, and Wei Young, who are all at UCSD at some point. And yeah, this is general preface about, so the things I chose to talk about in these Erdős lectures is structure and how structure plays an important part in various questions that come up in theoretical CS and in combinatorics and in math in general. And the talk I gave last Thursday in the math colloquium was about algebraic structure, and the one I'm giving a talk about today is about combinatorial structure. And then the one on Wednesday, that's going to be the theory seminar, is going to be more about geometric structure and how it sort of plays a part in machine learning and related stuff. So just to emphasize how different types of structures sort of plays part in different aspects of CS. Oh, good idea. Okay, so today is going to be about combinatorial structure because we're in the combinatoric seminar. And this is what I want to tell you about. So I'll tell you about the question that we were interested in, is understanding the structure of monomials of Boolean functions. So I'll tell you everything about it and what do I mean by that. And then I'll tell you why we actually cared about this question. So the motivation was trying to understand a very interesting conjecture in communication complexity called the Lagrange conjecture that I really like. And I thought this is about trying to understand some special case of it. We got into this question about Boolean functions. Then we discovered that also what we found out here has some connections to the union clause conjecture. I'll tell you about that. Then I'm going to give like a very quick sketch of the proof ideas, and then in the second part of the talk, I'm going to give you like a full proof of like the main technical thing we showed here. So yeah, so if you have any questions, please stop me and ask me that now. In the second half, either way is fine. monomials of Boolean functions. So this is going to be sort of our hero for the talk. So we're going to have an arbitrary Boolean function. So it's a function from n bits to a bit. So it's something that we all know and love, in TCS, in combinatorics. And what we're going to study is, we're going to write it as a polynomial. So it's going to be a multilinear polynomial. So I write it as a sum with no coefficients. So fs is some real number. It's a polynomial with the reals. And this is just going to be monomial. So I'm going to use x to the power s as just shorthand for just a product of all the variables in the set S. So, because we're over 0, 1, then any polynomial you can assume is multilinear, and there's just one way to do it, so this is unique. Okay? So really what we're trying to understand is what is the structure of polynomials that happen to compute Boolean functions. Unlike, let's say, a random polynomial computes some random function, not Boolean value. So, it's Boolean, what can you say about it? It's been widely studied for many different aspects. But concretely, what I'm going to focus about in this talk is, I'm going to say, let's ignore the values of these coefficients. Let's just think about the set of monomials. So all the monomials that appear here where the coefficient is not 0. So that's going to be sort of the monomials of this Boolean function. And really the question that we're going to study is, let's treat these monomials as a set system, a family of sets, ignoring the coefficients, and ask what can we say about set systems that happen to be monomials of Boolean functions. Okay, so that's the question. And then the reason why we cared about this question I'll explain later.
Is this related to Fourier expansion?
It is not Fourier. Okay, that's a very good question. So the Fourier is what you get if you replace it from 0, 1 to plus minus 1. Then it's Fourier. So that's important. This is not the Fourier. The Fourier expansion is also very interesting and leads to other questions, and I'll tell you some conjectures about Fourier later, but this is for 0, 1. So some of the basis actually is important.
And they are not related?
They are not related. Well, they're related in some aspects. If you care about degree, they're the same, but if you care about sort of other structure, then they're not the same. They're very different. Like for example, some polynomials, let's say parity, is very simple in the Fourier basis, just one monomial, but it's sort of very complicated in this basis. It's like all the monomials. So they're not the same.
It's a very simple transformation from one to the other, but this transformation changes, I don't know, the set M.
Yeah, it changes,
automatically
it keeps the degrees the same, but everything else changes. Okay, so let's look at two basic examples. So, how sort of polynomials look very different in this basis. So, end is sort of the simplest function in this basis. End is just a product of all the bits, 0, 1. And it just is one monomial.
And M is complicated in the Fourier.
And is exactly, yes. Exactly, that's right. And O is going to be a complicated function. You can expand it in this way, and you write it as a sum or Sabinov combination of monomials. You get all the monomials, basically. Well, except for the empty one. But essentially all the monomials. So O is complicated, End is easy. So parity is complicated. And what we care about is asking what are easy functions, in this language. What are functions that have few monomials? So that's going to be our goal. Our goal is to say, well, what is the structure of Boolean functions that happen to have few monomials, and what is the structure of these monomials? And I just want to point out that many Boolean functions, random functions or parity, are complicated. So we're not going to care about them. We're just going to care about simple functions. And we saw one example of a function that has just one monomial, end function. So we should ask, is that the only example, or are there other examples? Right? That's what we're trying to understand. Like, what are other examples of functions that are simple in this model? And now there is another very simple model that gives us simple functions in this model, which is a decision tree. So what is a decision tree? So we have a Boolean function. We say it's computed by a decision tree of depth d if you can build this tree, this binary tree with depth d, where every node queries a variable, and you go left and right based on the value of 0 and 1, and at the end, at the leaves, you're going to see an answer, 0 or 1. Or equivalent, you can think of it as an algorithm that adaptively queries d bits, one after the other. And always, the choice of, I guess, I don't know what it is. Good. Okay, so the choice of what bit to query next depends on the answers you got before. So the two things are the same. So here's an example of a depth 2 decision tree. And then you can write this as a polynomial. So why are depths D decision trees simple in this model? Because of the following claim that we're going to prove soon. It's a simple claim. It said that if f is computed by a depth D decision tree, then the number of its monomials is at most exponential in D. So if D is small, that's still going to be small. Okay? So why is this true? This is just by induction. So if D is 0, you query nothing. It's just a constant function. You have one monomial. Or maybe 0 monomial if you have a 0 function. What if your depth D? Then, well, by induction, you query some variable, let's say x1, and you go left or right. You go left, you have a depth D minus 1 decision tree here, and a depth D minus 1 decision tree here, and you just so you can write it's a polynomial. If x1 is 1, I go to the right. If x1 is 0, I go to the left, and then you just inductively expand the left and the right parts. Okay, so nothing too deep going on here, and you can verify this gives you exponential in D. And it's 3 because this has sparsity 2, this has sparsity 1. This is why I get this 3 to D. Okay. So if I have like a low depth or shallow decision trees, they also give me another source of examples for sparse Boolean functions that are computed by sparse polynomials, right? So we have decision trees, we have ends. So somehow we need a model that combines both decision trees and ends. So what's the obvious thing? You just put them both together. So this is a model that's called end decision trees. Okay. So what are end decision trees? We just try to sort of marry, ends and decision trees. So it's something that looks like that. So it's like a decision tree, but now in every node, you don't query the value of a single variable. You query the value of an end of variable. So like a big monomial. So maybe here I'm calling the value of the monomial x to the a. So it's 1 if all these variables are 1, and if 0 if at least one of them is 0. Then I go left and right and I keep going. And you can see in this example, for example, if it's still a depth to decision tree, so it doesn't matter what a and b and c are, it doesn't matter what monomials I'm querying, that's always going to have sparsity at most 4. Right? So the sparsity doesn't depend on what monomials I happen to query. So you just expand it in the same way, and then if I multiply two monomials, you get another monomial. So you can take this sort of claim we saw before, and it's just automatically generalizes the same proof exactly. If f is computed by a depth D and decision tree, then still the sparsity, the number of monomials, is at most exponential in D. And now, of course, this also captures both decision trees, and if I have to query variables, and it captures the end function if you just depth 1 end. So now the question is this a whole picture? And really the answer is yes. I mean, up to some quantitative losses, that's a whole picture. Nothing else can be done. So here's the theorem, more quantitatively. Then I'll tell you a bit about the parameters. So let's say I have a function from n bits to a bit, and it happens to have some number m monomials. So the theorem says that you can always find an n decision tree whose depth is like polylogarithmic in the sparsity and logarithmic in the number of variables. Okay. So this is sort of slightly more than what we had before. Before we had like log m here, and we get something that's slightly bigger, but polynomially bigger. So not too bad. So 2 comments on the parameter. So this polylog m, maybe if you were smarter, you could get this to be log m. And this log n should not really appear here. I mean, there's no reason why the number of variables should be even a parameter here. But for technical reasons, we do get it. So the conjecture I have is that the right side should be order of log m. But as you'll see that even if you get polylog m, if you could just get rid of this log n, that would already have interesting consequences. But for now, this is what we know how to prove.
So the lower bound is log m.
The lower bound is log m. I mean, they just come from like an n decision tree, or even a decision tree. Yeah. Okay. So this is what I want to tell you about.
It's not wood, maybe they are interesting.
That's even more interesting, right? Interesting examples are even more interesting than So, no, I think it is interesting because sometimes we have like very simple. We have conjectures, and usually conjectures come from like very simple example that we know, and we're hoping that they're the only thing that exists out there. And of course, if conjectures are false and we find more interesting examples, then I think that's sometimes even more interesting. So, but yeah, that's that's all the examples we know of.
Do you know that
the log n is unnecessary to fix m? Like if I tell you, okay, do m equal 5.
That's
Something like that.
essentially
Do you know that you don't need log n, or?
I think you can get n to be like exponential in n. So if m is a constant,
Yeah.
then I think you can replace this log n with m.
Uh-huh.
So you can, but then you lose something exponential in the sparsity.
Okay, so, but it's not unbounded as n.
It's not unbounded, no. You can always reduce to n being exponential in m. That's true.
Because each of the variables has to appear in some subset of the monomial.
Yeah, because you can basically if variables always appear together, just
Yeah,
identify the one variable.
Yeah.
And if you do that, you only reduce to like most m variables. Yes. And also we know that, I won't talk about this today, but you can talk about randomized decision trees and related stuff. And for this randomized model, this log n is necessary. So anyway, so the answer is unclear. But again, I think for the deterministic case, you don't need log n. But I don't know how to prove it. And if people care, I can tell you at the end how it comes up. Okay, so now, really this result comes from a slightly simpler result that, from now on, let's not talk about decision trees, let's ask about more simple questions. Let's say with this set system of monomials, what's the smallest size of a heating set for this set of monomials? So what's a heating set? It's a small set of variables that heats all the monomials. Why is it relevant? If you have a decision tree, then a path from a root to a leaf hits, you can show that sort of this set of hits of the monomials. And again, I can tell you about this more later, but that somehow is a core combinatorial question here. Everything is sort of very easy once you know how to do that. So really, so there's a definition here, just to make sure we're on the same page. If I give you any set system F, family of sets, H is a heating set for F, if it intersects all the sets in the set system, and if your set system happens to contain the empty set, then of course you don't need to intersect that. But let's just follow some small technical reasons.
Shachar, I didn't understand the explanation. We have a decision tree.
Okay.
Something appears only on this side.
Okay, good.
Left, you'll never meet.
Okay, let's say I have a decision tree. Let's say I take the path that always goes with zeros.
Okay.
So I get here, that's going to be a constant, let's say 1. So if I set all these variables to 0, let's say these d variables to 0, then the polynomial becomes constant. So these d variables hit all the monomials. And if you have n, you just choose one variable from each end. It's the same thing. Okay. Okay, so again, a heating set for a set system, just a small, hopefully a small set that intersects all the sets in a set system. And this is of the main, I'll say, technical result we proved. Now you see there's no n here anymore. So you have a Boolean function from n bits to a bit, and it happens to have only m monomials. Then this set of monomials have a heating set of size polylogarithmic in m. And again, log m is a lower bound, and we get like log m to the 5. And we didn't try super hard to optimize 5, but even if we tried, we wouldn't get it down to 1. But it was 5. And you see, so here n doesn't really, so n somehow only comes when you try to convert this to this decision tree model, and the way to do that is sort of intermediate model, and somehow there's some losses in the way. Okay, good. So now I want to tell you about this result, and in the second part of the talk, I'll give you a full proof of this result. So what I want to tell you about now is why we cared about this result, and how it connects to this Lagrange conjecture, to the union closed conjecture, and some taste of what comes out in a proof, and then I'll give the full proof in the second half. Any questions about the definitions, or what the result is, or anything else? So what's the connection to the Lagrange conjecture, which was our original motivation? So maybe, what is the Lagrange conjecture? If you haven't heard of it, then that is one thing you can get from this talk. It's a really cool conjecture. It's also an open problem that came up in communication complexity, but it also came up, even before in graph theory. It came up, in geometry, in other areas, in extended formulations. It's really sort of a very fundamental question that asks, if I give you a matrix, and this matrix is low rank, and it's Boolean, what is the structure of such a matrix? So it's a very, I think, clean mathematical question, and it comes up in various applications. And the short answer that we don't know, but we have some conjectures. So what's the setup? So I give you a matrix. It's a Boolean matrix. So it has 0, 1 entries. and its rank is R. And here it's important that the rank is computed over the reals. If you go to like small finite fields, the answer changes dramatically. So it's important that the rank is over the reals. And assume the rank of this matrix is really low. So R is much less than n. A random matrix should have high rank, maybe close to n. Assume the rank is really low, much below n. What can we say about the structure of such low rank Boolean matrix? That's a question.
What is the sparse density of the matrix?
Oh, that's a very good question. So that's a 50-50 even. Half zeros, half ones.
I'm looking at density.
Could be
What
dense.
is the
Not sparse.
Yeah, not necessarily sparse. For sparse, you can ask other questions that are related, but think about dense. Yeah. So here's one way you could do it. Like a very naive way of getting like a rank R matrix. You take your matrix and you sort of partition it into a small number of rectangles. And rectangles could be what's called combinatorial rectangles. Rectangles is just a submatrix, rows and columns. But of course, when I draw it here, it's easier to draw them into like geometric rectangles, but they don't have to be. So imagine you sort of partition your matrix into rectangles, and let's say you partition it into R rectangles, and you call each rectangle either 0 or 1. So maybe this is 0, this is 1, and so on. So the claim that every way of doing that will give you a matrix whose rank is at most R. Why? Because I can take my matrix and write as the sum of these rectangles. Each rectangle either an all 0, so it has rank 0, or it's a 1 rectangle has rank 1. Because the rank is subadditive, the rank is at most R. So really the question here is this the only way? And the conjecture that will, up to some losses, that should be the only way. Okay? So what do we know about this conjecture? So maybe before that. So here's the actual conjecture. This is sort of from a paper of Lovett and Shachar of the late 80s. And it says that, well, if you have a Boolean matrix whose rank is R, then you can decompose to some capital R, and capital R is slightly more than small r. It's quasi-polynomial. I'll tell you why quasi-polynomial actually makes sense here. I mean, that was not the original conjecture. The original from the 70s conjecture something stronger than that, but then people come up with counterexamples. And that's sort of also interesting, finding examples. But some quasi-polynomial number of monochromatic rectangles. Okay. So again, think of capital R as slightly more than small r, but not much more than small r. So the original conjecture that people came up with in the 70s, motivated by connections in graph theory between chromatic number and rank with the adjacency matrix, were much stronger. The conjecture maybe capital R should be linear in small r, or maybe polynomial. But people found counterexamples for them. And the best examples we know of today is of matrices whose rank is small r, but to partition them into rectangles, you need at least r to the log r rectangles, which corresponds to this value c being 2. So the conjecture that maybe c is not 2, maybe it's 5, maybe it's 10, we don't care, right? Any constant. So what do we know about this conjecture? So there's a trivial bound that is a nice exercise that it's exponential in small r. And a few years ago, I proved something that's sort of slightly better. We could be essentially exponential in root r, not r. And that's a better to know in general. And this is still exponentially far off, than this sort of quasi-polynomial bounds. And sort of people said, well, since we don't know how to solve this question in general, let's try to work on special cases. Because maybe we can get more progress in special cases. So there is a very nice generic way of getting special cases for matrices, which is called lifting. But to explain lifting, it's actually easier if we sort of switch in our mind between thinking about matrices and thinking about sort of communication games. Well, they're the same thing, just that it's a more convenient sort of framework. So what is a communication problem? It's a function that takes two inputs, capital X and capital Y, and outputs 0, 1. And you can think of it as I give you this big matrix, and one player gets a row entry, and one player gets a column, and then to decide what's the entry in this row and column. So it's exactly the same as a matrix, but it's just a more convenient language to describe things, this type of constructions. And the general type of examples is called lifted functions, and it's constructed in the following way. So it has two components. There is a Boolean function, we think of an outer function. It has just one input of n bits. And there is a gadget. So a gadget is some function, usually simple, that takes an x input and a y input and outputs, a bit. And how do you compose them together? So you build a big function called lifted function, takes n copies of x, that's one player gets. The other player gets n copies of y, and they compose them in this way. So they apply the gadget to x1 and y1, they get the first bit of the input to this function small. They apply the gadget to x2 and y2, and they get the second bit of the input to small, and so on. So this is called lifted function. There have been tons of research on them. We know a lot of interesting properties of them, and if the gadgets are sort of complicated, then we also know this log-rank conjecture is true for them because there are a lot of connections between the communication complexity of these lifted functions and what's called sort of the query complexity of this small function, small f. But when the gadget becomes very, very small, very, very simple, these connections sort of break down. And what we cared about here is looking at what is probably the simplest gadget, which is the AND gadget. So think of the gadget where x and y are just bits, are also bits, and we just AND them. So the two-party function or the communication problem we get is one player gets an n-bit input x, the other player gets an n-bit input y, we AND them point-wise, and we apply them to a small function f. So how all of this is connected to what I told you about so far? Turns out that if you build this matrix and you compute its rank, it's exactly going to be the number of monomials of the small, of the function f. So really, if you want to understand log-rank conjecture for these AND functions, for this special case of functions, then the rank of these matrices is exactly the number of monomials of the Boolean function. So if you can prove something structural about Boolean functions with few monomials, there is a hope of proving something structural about these types of communication problems.
Can you say a word about how to prove it then?
I can show you one direction, it's easy. The other direction is also easy. But I need an eraser. Okay, good. Yeah. So let's say I have a function on let's say z bits, z1 up to zn, and it's some sum fs z to the s, right? And now I want to look at the function that I apply to this two-party function, right? So it's going to be x1, y1, xn, yn, and that's going to be, well, the same, sum of s, fs, x to the s, y to the s. And what is this? If you think of in terms of x and y, that's a rank 1 matrix. That's rank 1. And you can show this is going back also. So, yeah. So it's not a very deep claim. So this was really our motivation for studying this question about monomial structure. And what we can prove is the following result. Just basically plugging in the result I told you about decision trees, that if this matrix happens to have rank small r, then you can find a decomposition where the number of rectangles is now 1, and we really care is this quasi-polynomial in R. So we didn't get C in this process 5 and not 2. But we get this annoying log n here that we don't have to get rid of. And that is why I care about getting rid of this log n. Because if we can get rid of this log n, even if this 5 became 100, this would prove the log-rank conjecture in the first sort of general case that sort of doesn't just follow from query complexity. Anyways, that was our motivation. Let me know about are there any questions about this connection? Otherwise, I'll tell you about another connection to union close conjecture.
Okay. So with this log n term, is this bound still like how do you compare this bound?
So it's sort of there's basically a case what we don't know how to prove the log rank, which is if a Boolean function is like super sparse. It's like maybe it's an n variables and has like log n monomials or polylog n monomials. So it seems like these super sparse Boolean functions should have tons of structure, but we don't quite know how to utilize it. But the log-rank conjecture, if it's false, it's probably false for very structured matrices. So if this is false, that's also very interesting because we show that maybe a way to disprove it is to construct something very structural. There was a related conjecture about the log rank for like what's called randomized communication complexity, and a few years ago this was disproven. And the counterexample was also this type of lifted functions, not with AND, with XOR, but they had to use the lot of structure to construct the counterexample. So it could be this is false, the logarithm is false for like structured input, which is really what it's trying to argue about. Because random matrices are going to be high rank, high complexity, high everything. Yeah. I don't know. Okay, so what's about connection to the union clause conjecture? So maybe first some definitions. So we have again a set system F, and we say it's union closed if whenever you take two sets in your set system and you union them, it's also in your set system. It's closed under unions. And the union clause conjecture of Frankel from the 80s is the following very simple but sort of notoriously hard conjecture. It says, let F be a union closed set system, then some element should belong to half the sets. At least half the sets. Yes. Yeah, at least half the sets. And why is this natural? Because if you take all sets, out of n elements, then every element is union closed, and every element belongs to exactly half the sets. And this conjecture basically says that this is the best you can get, or the worst, I don't know. But of course, everybody worked on it, everybody failed, and we don't know. So I'll tell you what we do know, and that's more or less the most general thing we know. I mean, there's some small improvements that are known, but it's embarrassingly the best that we know in general. It's basically based on the following claim, whose proof is I'll show you the proof, it's a 3-line proof. It says, let F be a union closed set system. And let's say M is the number of sets in your set system, then it has a heating set of size essentially log M. So in particular, one of the elements is in at least 1 over log M fraction of the sets. And you can improve the constant by a little bit if you work very hard, but that's all that we know in general. So what's the proof here? Okay, this is the corollary. What's the proof? You see, it's going to be a simple proof because it's going to fit here. And I won't change the font, I'm not going to cheat. So let's say H is a minimal heating set for this sort of set system. So because it's minimal, it says that for every element in this heating set, X, there is some set in your set system that intersects this heating set in just this one element. Because if this wasn't the case, you just remove it from the heating set. It's not necessary. So this Sx here, intersecting H in just the element X. And because F is union closed, and it takes then every union of these sets is also in the set system, and you intersect this with H, you get all the subset of H. Maybe except for the empty one. So that's it. That's the proof. So, see. Embarrassingly, that's all that we know, basically. So again, I think there is a work improving this one to a slightly smaller constant, but I think it's a lot of hard work improving this one. I don't know. Maybe people here know of this.
Yeah.
Yes.
We talked about this.
Yes.
So I don't think he improves the hitting set bound, but then just uses extra arguments to improve the thing you care about, which is the frequency of an element occurring.
So do you remember what they improved one to?
Like there's I think the constant improvement by like log of 4/3, something like slightly bigger than 1. Just a constant improvement.
I see. Okay. So again, if people here don't know about this conjecture, then maybe someone can solve it. We should be able to prove it. Doesn't seem that hard. Or maybe it's false. No, maybe we have the counterexample. So what's the connection between this and what we studied? So now we say, let's say I take a set system that is like the set system of monomials of a Boolean function. So the question is this sort of related to being union closed? And I argue that there is some connection. The connection comes from the following fact. Because f is a Boolean function, then f squared is f, because every value squared is 0, 1, you get 0, 1. Now let's expand f squared. What is f squared? So you go over all pairs s and t, you multiply the coefficients, and you have the product of the monomial, so it's x of s union t, and that should be equal to the original function, right? So if somehow we were super lucky, and there were no cancellations in the coefficients, somehow no coefficient here, so when you sum them up over all s and t given a union happen to cancel to 0, then we would get a union closed set system, right? But of course, that's not the case. I mean, there are many, many examples where you get tons of cancellations, but really what we showed is that in some, let's say, qualitative way, such set systems are not super far off from being union closed. Like, for example, they still have, small hidden sets. But the proof is going to be sort of a bit more involved than the proof for union closed. And I can also show another connection, which is the following claim. So if you give me a union closed set system, then I can find coefficients for these sets such that if I create a polynomial, it's going to be a Boolean function. And the question is, what can we do with it? I don't know, but these are functions, the Boolean functions happen to have no cancellations when you square them. And one hope I have is that maybe we can use some tools for Boolean function analysis to try and study the union-closed conjecture using this type of connection. So again, we don't have any results on it, but I think it's sort of an interesting direction to explore. So this is it about the union-closed conjecture. Any questions?
So how do you make this fact? These are
So Gil, what's the question?
okay. You didn't prove the claim.
No, I didn't prove the claim. We sort of do it greedily. Sort of go. It's just a greedy process.
And these coefficients are integers or not?
The coefficients?
Yes.
Yeah, they're going to be integers.
Only.
They're going to be integers, yes.
And at each level you pick to make it hit 0 or 1 to make sure that it is
Yeah.
non-zero.
Yes, exactly. It's an exercise. It's a naive, greedy way from what to the top. Yeah. And because every time you have the two options for 0, 1, at least one of them will not be 0.
Yeah.
Yes, so some people already prove the claim. Good. Okay, good. So proof like this. Now I'm a bit debating because I'm going to give you the full proof, in the next hour. So let me just go quickly through some of the proof ideas, and then because I'm going to give them in much more details, in the second half. So this is what I want to focus from now on. It's about these are the main combinatorial results, and you take an arbitrary Boolean function, you write as a polynomial, you take the set of all its monomials, and you want to prove that this set of monomials has a hidden set of size polylog n. Again, you know about this 5, we don't know about the 5, some polylog n. So, first step is to rephrase this question in a language that we're more used to working with in Boolean function analysis, which is called certificate complexity. So, what you're trying to prove, you haven't done it so far, is that this set of monomials has a small hidden set. And I'm claiming that's the same as saying that if I take these variables and I set them to 0, the polynomial becomes constant, right? Because if I set of variables that intersects all the monomials, and I set all these variables to 0, so now all the monomials become 0, so the polynomial becomes constant. Okay. So this is what we call a certificate. So this is going to be, H is going to be a certificate for this function at the input of all zeros. If I take the all zeros input, and I fix these values to 0, then then this fixes the value of the function. Right? The rest of the variables don't really matter. And this is how we denote it. This is going to be the side of the certificate of f at the all zero input. So let's define it a bit more generally.
Oh, quick question.
Yes.
What is C?
Okay, I'm going to C for certificate.
The setup.
See, I'm going to define this in the next slide. Okay, good.
Oh, question.
Yes.
Is it possible to have a certificate but not can you have certificates that don't come from something like this, or?
No, so certificate always for you, but I'm going to define certificate in the next slide. So if it's not clear after I define it, then ask. Okay. So here's a certificate. Okay, good. So I have a Boolean function, have some arbitrary input, maybe not of 0, some arbitrary input. A certificate for x is a set of coordinates, S, such that if I set these coordinates according to the value of x, the function becomes constant. Okay? So this is a certificate. And equivalently, it said if you take any other input y, and it agrees with x on these coordinates, then the values must be the same. Okay? So this is what we call a certificate. So is the definition clear now?
I just wanted to know
Yeah.
if something can have a certificate without having that as a hidden set.
Yeah, so certificates and hidden set are two different things. So hidden set is for set systems, and certificates is for Boolean functions, and they only coincide if the input happens to be all 0. Otherwise, they don't have to coincide.
This corresponds to a subcube in which the function is constant, the same as subcube containing x, in which the sum of the function is constant.
Exactly. And again, that's a notation, Nori. So C of f of x is the smallest size of a certificate for x. So it's a number, right? And our goal is, once we rephrase the hidden set of certificates, is to say we want to bound the size of the certificate for the all 0 input. Good. So how can we do it? So there is a general connection that we know between certificates and a different quantity called block sensitivity that I'm going to define now. So block sensitivity for a function at an input x is the maximal number of pairwise disjoint blocks of inputs, coordinates, such if I flip each one of them individually, I change the value of the function. So for example, if this is my input x, and let's say I have this block here, b1, and this block here, b2, and if I flip all these bits, I get a different value. Then let's say f of x is 0, and f of x XOR b1, bi is 1, right? Then both are sort of sensitive, and I want the maximal number of pairwise disjoint blocks. So why is this connected? Because of the following connection. It holds not just for 0, for in general. It says, if I have, let's say, 2 disjoint blocks, and I want a certificate, I have to have at least one variable here and at least one variable here. Because if I have no variable here, I cannot distinguish x from x when these bits are flipped. So in general, for every input x, or in particular for the 0 input, we want to say, well, the certificate is at least a block sensitivity. So if you want to prove this is small, maybe it's a good first step to prove this is small. Right, and maybe you can utilize that. So you want to bound this. And you can show the following thing, going back to the polynomial landscape, that this block sensitivity at 0 is exactly the maximal number of pairwise disjoint monomials. When you write your function as a polynomial, you take all the monomials, just what the maximal number of monomials that are all pairwise disjoint. So these two things are the same, so why should this be small? Because of the following type of intuition. If I give you a sparse polynomial that happens to compute a Boolean function, then the monomial should have tons of structure. There should not be a lot of disjoints. That's like the general intuition, and then you can prove it. So the first thing I want to prove to you in the second part of the lecture is the following lemma that said, if I give you a Boolean function, it's computed by a polynomial with m monomials. The number of pairwise disjoint monomials is at most polylog m. More than polylog m. Okay, so now that we know that, so we can bound this block sensitivity, but of course that's not enough.
So this is very different than general function.
Yes, this is a very different general function. Yes, this is really using the fact it's a Boolean function. Of course, if it's a general function, some variables, it's going to be a function, but not disjoint. Yeah, this is in fact it's Boolean. Yes. So we sort of overcame the first obstacle, and this block sensitivity was large. We sort of doomed, so it's small, it's good, it's not enough. So what can we say? Well, we know in general, let me just say this here. In general, we know people have been studying this block sensitivity and certificate to infinitum, so in Boolean function analysis, and we know tons of things about them. So in particular, if we take what's called the block sensitivity of the function, which is the maximal block sensitivity of the function on an input x, and similar to the certificate maximum, then we know the two things are connected after polynomial factors. But this was first proved by Nissan and Segedi in early 90s, and this concept is of sharpened sense and like a sequence of forks. So that maybe is one approach. We know so far this block sensitivity of 0 is small. If for all the inputs it would be small, then we could use this connection, we get the certificate to be small for all inputs, will be done. So maybe we should do that. If we can bound this for all inputs, we are done. But unfortunately, this is not true. Here's a counterexample. End, right? End is like the simplest function that is sort of, with few monomials, one monomial. And it really depends what input you choose, right? If the input is all 0, then, and you want to flip the input from 0 to 1, you have to flip all the bits to 1. So you have like one block. But of course, if you're in the all 1 input, and you want to flip it back to 0, you choose each one of the n bits and flip them back to 0. So it becomes like really, really big block sensitivity. So suddenly we're in this sort of landscape where the inputs start to matter if they're all 0s or all 1s. So it turns out that what you need to understand is that in this end model, there is an asymmetry between 0s and 1s. So flipping somehow from 0s to 1s is okay, flipping from 1s to 0s should not be okay. So we want to define analogs of this block sensitivity and certificate using this type of asymmetry. And again, I'm not going to give you, I'll write some definitions here. I'll give them more details in the second part. But there is sort of a natural way you can extend these definitions of block sensitivity and certificates, where you're allowing to flip zeros to ones, but you're not allowing to flip ones to zeros, and satisfy the standard connections. So now we could hope to say, well, and again, ignore these technical definitions for a second, just think of this sort of written symmetry. So we can ask, so here's going to be like a new plan, move it to these new complexity measures, and say, well, we can sort of prove that the first one is this sort of block sensitivity that's monotone, or going from 0 to 1s, is still small. Maybe we can prove something like this Segedi and get this type of result. Right? This would be a new approach, right? A right approach. Maybe you could just take the original proof that works for the symmetric case and just make it work for the asymmetric case. But, and the part 1 you can prove, but part 2, I mean, maybe it's true, but we don't know how to prove it. Because, in particular, if you take the classical tools people have developed in Boolean function analysis and try to apply them to these asymmetric measures, they just fail. They don't work. And they don't work for, not just for technical, but for good reasons. I mean, there's sort of inherently some things are different in this case. Maybe
then what is the connection between ZCF and CF?
Okay, so ZCF is actually what we care about, because for zeros are the same. So they happen to agree on the zero input, yes. By the way, Gil, maybe you would be interested. This is also connected to quantum computation, because in quantum, what we care is about bounded functions. And also for bounded functions, all these classical tools fail. So this is sort of a simpler model, but also all the classical tools fail. But actually, what we can prove here is that part 2 is true for if we also remember that we're working with sparse polynomials.
It's probably more interesting even for me.
That is also true, yeah. Also for Michael, yeah, you're right.
We are the
Quantum side. But well, one is for, one is against, right? So, yeah. So, but we can prove too if you also remember we're working with sparse polynomials. And again, so turns out what we can do, and I'll tell you much more about it in the second half, is that you can define what's called fractional versions, or like the relaxed versions of this model of these measures. And the main thing we prove that is sort of using new here is sort of bounding the integrality gaps for these fractional measures, even in these asymmetric cases. And actually, this is something very recent that so we haven't. You can actually prove this also for the bounded case, which is also related to these quantum questions. So this technique is more robust than sort of previous techniques in Boolean functionality, because this can actually adapt to bounded functions as well. Bound these integrality gaps, and then so you can put everything together and get things to work. So again, I'll tell you much more about it in the second half, but let's just with a high-level picture. So we move from like the standard complexity measure to these sort of asymmetric ones. We move to fractional relaxations, and then sort of, I'll say the one thing, that step 1 and step 3 sort of followed by standard techniques in this area, and step 2 we sort of invent from scratch. That's sort of these completely different new techniques. Okay, good. So this is what I want to tell you about for now. Just to summarize.
So,
yes.
maybe I missed something, but there was this Huang sensitivity
Yes.
theorem. Is it fixed, let's say?
It's not really, because this is really about sensitivity. Once you move to block sensitivity, many of the obstacles disappear there, so it's not really related. You could relate it, but there's no reason to. You just add in complication for no good benefits.
Sensitivity is a simpler concept, or this was Noam's insight. That block sensitivity, in fact, works better. He was able to prove that
Because it's hereditary. It's hereditary in a stronger way. Yeah. So just to summarize, so the main message is that if monomials of Boolean functions have tons of structure. So what we proved here is that they have a small hidden set. You can use this to design an decision tree computing the function. So there's a lot of structure there. Probably there's more structure than the one we discovered here. So I think that's interesting to explore what other structure they have. Very quickly about the parameters, like I already told you about this. I think this log n should disappear from here. This 5 should become 1. Okay, so both I think are interesting to try and explore. And this is also, Gil, related to your question. What happens if we go to the Fourier basis, right? Because you can ask all the same questions, not in the standard basis, 0, 1 basis, but in the Fourier basis where the variables are just plus minus 1. Right, so you just take a polynomial. Let's say I'm going to interpret bits not as 0, 1s, but as 1 minus 1. And you can still do a polynomial expansion. It's called a Fourier expansion, and you get the same questions, right? So this is usually called the number of the sparsity here is usually called the spectrum. It's called Fourier analysis. And so here, unlike in the Boolean case, you can do a change of bases, and it doesn't change this. It changes what are the monomials, but it doesn't change the number of them. So whatever structure you might hope to find here should be something that's invariant to changing bases. Okay. So here is sort of the analog conjecture here. I mean, and this is not the conjecture that we came up with. The conjecture existed before, and people know of it, but nobody knows how to solve it. And it said the following thing: if the side of the spectrum of a Boolean function is, let's say, R, so it's the number of monomials, in these Fourier bases, then you can do a change of bases such that under this change of bases, you have a small hidden set. So the added complication here compared to the end case is because here the symmetry group is larger. It's a, changing bases. You need to allow changing bases and find a hidden set. In the end case, the symmetry group is small. It's just Sn, just permuting the coordinates. So then it doesn't really matter for hidden sets. But here it does make a difference, and you can show that you need the change of bases. And again, this is like wide open.
Who asked this question first?
So there was this paper about 10 years ago about log-rank conjecture for XOR functions, and they asked this. They showed this is equivalent to log-rank conjecture for XOR functions, and they could prove it in a special case, like if it's a monotone function, if it's a logical polynomial, but in general it's open. You can get a bound here that is root R. The best bound here is root R. And again, but with conjecture polynomial.
Now, there were some papers about the structural functions with small space.
Yes. But they usually ask different questions. They ask, if you have a function whose like spectral norm is small, then you can write as a sum of a few monomials. But first of all, they lose something exponential. So the quantity bounds are the first one were powers of exponential and single exponentials. But so they give good qualitative answers.
What are they?
Maybe cones. You were doing the first one, trying to understand. So this has some connection to other areas of math. But now I'm blanking out on the exact connection. But there was other in native combinatorics, like Sanders had a result, and I think Amir Shpilka had a result with somebody, and there was a bunch of results on the things trying to improve the quantity bounds.
Maybe also you made it.
Maybe, possibly. But
Sanders has something.
But all these things do something exponential, which is the right answer for the question they're asking. But for this question, we don't know the bound, sort of. Okay. Anyways, so this is equivalent to what's called the log-rank conjecture for this other special case called XOR function that sort of people really care about. And again, for the last thing is maybe for this union close conjecture. I think it's just an interesting direction to explore. You can now rephrase the union close as a question about Boolean functions with no cancellations. And now we can say, well, could we hope to use any of these sort of fancy tools we have, hypercontractivity, anything fancy, to say something interesting about union close? So maybe, I don't know. So this is it for the first half of the talk. So I think now is a good time to take a break, and then we can continue. The second half will be on the board, and I'm going to show the proof of this main combinatorial.
So let's make it 10 minutes. So that's 12 or 4. Okay.
אני פה, אנחנו הולכים לאכול ערב ב-6. רגע, נתי, מתי אנחנו יוצאים בשביל המסעדה היום? איזה שעת אתם? יוצאים פה ב-6? אני פה עד 6.
ואתה כאן גם ברביעי?
אני אהיה פה גם ברביעי.
אז אולי ברביעי?
אני תוכלי לרביעי, אפשר היום של רביעי.
רביעי עבדתי. טוב.
בסדר, אני רגע. אבל לומד עד 2, אני לומד עד 2. אתה אוכל לפני,
אני חושב שהבול והמאה